Hello, can you guys hear me? Okay, cool. Okay, we can probably get started. Okay. Mm, mm, mm. Okay, so last time we talked about the greedy algorithm, and today we're gonna start on basically the continuation. Well, it's not really the greedy algorithm, but we're gonna talk about something which is related to the greedy algorithm, which is called dynamic programming. Okay, dynamic programming is a very generic and also very powerful method. It has a very wide range. Okay, so um, I think in this class we will. I think this week and next week we're gonna talk about the dynamic programming, and we're gonna probably introducing some like easier to medium kind of the DP problem, and the DP itself can be very complicated. But I wanna like show you at least some of the idea behind the DP, which is very important. So um, to start off the topic of DP, we let's just last time we mentioned um, certain problem like greedy is unable to tackle, right? So we basically we start this topic by showing one of this example. That's kind of like intuition why we want the DP in some cases. So okay. So this problem essentially is called a knapsack problem. Okay. So generally speaking, is thinking about if you planning a trip for example, for camping, right? So you have a knapsack, then you have a knapsack, then you want to bring things with you to the camping, right? Then knapsack has a total capacity, right? So suppose this total capacity is called W. Then you have a list of the item you want to bring, right? Right. So suppose each item they have uh, uh, their capacity and the value, right? So for example, each right. So then essentially you can think about you have something like you know um, okay. C1 is the capacity for the first one and the value for the first one, and C2, C2, until you have like Cn, Vn, right? The problem is trying to find out, find a subset of, basically to find out what item you can bring in such a way that it satisfy the condition is the total capacity will be less than the given capacity, or the sum of the capacity less than or equal to the total capacity. Well, think about like, you want to bring lots of stuff, but maybe the container is only big enough to bring, you know, limited stuff, right? So then also you want to maximize the total value, right? You want to maximize the total value of the one you want to bring. Okay. Then knapsack essentially this is a kind of like the problem setting, but under this problem setting, there's a different variants on the knapsack problem. That's basically is so the variance essentially is on the item. It's really on the restriction on the item. Okay, it's on the restriction on the item. So we will we will see like we will talk about two of them. Then depends on the restriction, then you will probably apply different, the technique, right? So the first one, what we're going to talk about essentially is what sometimes we call the fractional knapsack problem. Basically, the idea is for the list of the item, you have basically you can choose if the item doesn't fit into the knapsack, you can choose partial of the item. Okay, that's actually the reason we call it fractional. Basically means that you can the item can be taken as a fractional. Okay, so let's see a concrete example. So suppose the total capacity is equal to 10. You have 4 items. Okay, so this is the capacity. This is your value, right? So this one is 2, this one is 4, and this is like 3. This is like 5, and this is like 3. This is like 4. This is like 2. This is like 3. Oh, actually, this is not a good example. Let's see. Let me change this one a little bit. Okay, change this one a little bit. So okay. So okay. So under this setting, so intuitively, can you guys think about what kind of strategy you want to do? For example, which item you want to pick first and why? Since we only have 2 people, so you don't have to type. You can just speak up. It's not. It's just like, yeah. You have 4 items, right? So the capacity and the value. Like intuitively, like if you want under the limited capacity, if you want to bring more value, what kind of the intuition you will do? Like in this case, there's no like. I mean, I'm just saying, like, don't be afraid to share your thoughts, right? So it's like, that's actually mainly like computer science. The problem is coming from really like a daily life. You use your like common sense, use your intuition. Anyone? Nobody? Okay. Okay. So, all right. Let's think about this one. Okay. So, if you want to bring more value into the knapsack, right? One of the way is to compare is you calculating the ratio essentially is the value versus the capacity. So this one they will tell you the unit value you're gonna bring in for each capacity, right? So basically is for every one capacity, how many value this item will give you, right? So for example, the ratio, if you calculate the ratio, so this one it will give you 1.5. This one it will give you something like 1.7. Well, 1.6667, right? 67, something like that. So this one, it will give you 1.3, right? This one will give you something like 1.5. Okay, so by this value, clearly you will know, okay, I probably should take the second one first. I should take my second one first, right? So take the second one first, then maybe take the first one and the fourth one. Then now we will have basically is the order of the so essentially is by calculate the ratio, you can apply some kind of like the greedy kind of like choice. Essentially, is you take the higher ratio first, right? So from the greedy, you will first take the second one, then then you got three, then you're taking either the second one or the fourth one. No, sorry, the first one or the fourth one. So that will give you 4, 2, that's 6, so you got to get a 9, right? Then the last one, you only take, because at this time you only have 1 unit left. So you can take 1/3 of the third one, right? So that's kind of like, so that's kind of like, the, oh, sorry, I don't really like, yeah, let me just do this. Take basically, right? So, so then you can kind of like prove this will give you the optimal solution, right? Because whenever there's an item with a higher ratio, it's always optimal to pick that one because you can pick a partial. So it will never be like optimal if you pick the lower ratio one. That's the reason for this particular problem. We have a very nice, greedy algorithm to solving that. Essentially, say let's just calculate the ratio, then sort them, then pick them from the highest to the lowest. Then just keep filling until the sum of the capacity. Well, until the sum of the capacity is as long as the sum of the capacity is not larger than the total capacity, you can keep filling until the last one. Last one you can probably pick just a partial in such a way, it will basically add it up to the total capacity, right? So this makes sense. Like for example, some of the item can be partial. For example, like water or maybe the I don't know some other things can be taken partial, right? So this works very well for the greedy. Okay, let's try to think about when this guy gonna fail. Okay, so let's think about the second problem, essentially also the knapsack problem, but with a slightly different setting change. This one probably more close to our daily life. This is called the 0-1 knapsack problem. Essentially, is for item they cannot be partial. For example, if you say you bring a camera, then it's unclear, what does it mean by 1/3 of the camera, right? It doesn't really make sense. If you bring a camera, you either bring the camera or you not bring the camera, right? You can't say I bring 1/3 or 1/2 of the camera. That makes no sense, right? So similar problem setting essentially say now each item you either take it or you not take it, right? Right. then um then let's look at the following example. We will show the greedy will fail. Okay, so let's still think about the total capacity is 10. Let's have this 4 item. So the first one capacity is 8, value is 9. Then this one is like 4, is 4, 3, 3, 3, 3. All right. So if you calculate the ratio, then this one will be 1.125. This one will be 111. I'm kind of like intentionally make the case, okay? So if you apply the greedy choice, you will take 8, right? You will take 8. You will take the first one. Then you leave the total value, the max. You leave the value. The total value is is 9. However, you can probably, spot, the optimal solution in this particular case is not taking 1. Just don't take 1. Just take 2, 3, 4. Right? Take 2, 3, 4. You will get your total value is 10, which is better than the 1 if you just do the greedy. Okay? So this is a very, very classical example, basically show, I think the problem is if you take the greedy, then because in this case it's not allowed fractional. That's reason if there was any like a leftover space, you may not be able to like to leverage. Unlike so which means you could potentially take a less optimal solution at the first, but then added more, so which as a result you can leverage more of the capacity, hence increasing the total value. So that's kind of like where this one fell. Okay, so then knapsack inside of the DP is like median kind of like level. Okay, so that's reason we will talk about how to solve this problem next week. But I want to let you guys see this problem first. Then also, in terms of the knapsack, there's some other variant. For example, so far we see 2 examples. One is the fractional, essentially item can be taken as a partial, or the 0, 1. 0, 1 essentially every item you either take it or you leave it, right? The third one is just imagine you have a different type of item. Every item has unlimited like quantity. This is a scenario like if you go to supermarket, you have your shopping chart, right? Your shopping chart is also has a limited capacity, but just in this case, you can imagine all the items you want to buy is kind of like unlimited quantity, right? You can fill in, but now you have to think about how you can fill in your shopping chart in such a way you can, again the maximum value, right? So that's a third type essentially. So you can think about it's all working on the like the restriction on the item. We start with the fractional to 0, 1 to unlimited. Then clearly you can think about there was something in between, right? For example, between 0, 1 and unlimited, there was basically the limited one. Essentially, it says that for each item, there was a multiple of them, but there was not unlimited supply. There's only limited of them, right? So it's called like limited knapsack problem. And also, the final one is you can mix them together. For example, you can say, oh, some of the item is you can take a fractional, some item you have to take 0, 1, some items they are unlimited, right? So that's kind of like a more close to our real life because we do have like a different type of item. So but understand how to solve 0, 1. You kind of like for the other one, it's kind of following similar idea. Okay, so but I want to use this one as an open, basically try to show you. Okay, dynamic DP is it's a more generic method than greedy. Greedy only apply to a a subset of the problem, they have to satisfy certain conditions. Okay, DP will kind of like doesn't really have that kind of the restriction. Okay, so okay, so to start off with the introduction for the DP, we're gonna start by looking at one of the problem. Let me just give you 1 minute. Let me pull out the problem. I want to start with something that's really, really easy. Okay, so yeah, this is the one. Some of you may or may not see this problem already. So okay, this one is called climbing stairs. This one is called climbing stairs, and this one, well, just temporarily ignore this solution. You can just look at the the left hand side. Okay, so basically say if you are climbing a staircase, right, you take n steps to reach the top, right? Every time you can either climb 1 or 2 steps. Basically, they're asking about how many distinct ways you can climbing to the top. Okay, climbing to the top, right? So they give some examples. Say when n equal to 2, there's a 2-way, right? You either do 1 step plus another 1 step, or you just do directly 2 steps. Similarly, when n equal to 3, you can do 1 plus 1 plus 1, or you do 1 plus 2, or you do 2 plus 1, right? So the question itself is relatively straightforward, right? So let's think about how to solving this problem. Okay. Okay. Again, at the beginning of the last week, we talked about, basically is this set of the problem satisfy one of the conditions. Essentially is, it has some like input, right? It has some input. In this case, you have input n, which is number of the stairs, right? Then your answer is kind of like a function of this input, right? So that's actually the reason. Suppose we can say an is the number of the solution, of n stairs. Okay. So we already see, when n equal to 1, a1 equal to 1, right? When n equal to 2, this is equal to 1 plus 1 or 2. So a2 equal to 2, right? When n equal to 3, we say, okay, we have 1 plus 1 plus 1 or 2 plus 1 or 1 plus 2, right? So, okay, so this is something we need to talk about, okay? Let's look at the first 2 solutions. So one way you can think about this one is, so the solution here basically says, the sequence of the steps they're going to take. Then if you're looking backwards, what does this one means is the last step taken is 1 step, right? The last step taken is 1 step. Right? If the last step is 1, then it has to come in from 2, right? It has to come in from, the 2. Then you're looking at this guy. Sorry, this is the wrong arrow. You will find, oh, that's exactly corresponding to this solution in n equal to 2. See, right? Okay. Let's look at this one. This one you can kind of like thinking about is the last step, this one taken is 2. Right? If last step taken 1 is 2, then the previous state will be 1. Right? Because you can only go from 1 plus 2, that is 3. Right? So basically means this one, what? Oh, okay. This one corresponding to this. Okay. So this is a very, I mean, I'm using this very simple example, but this is contains some very deep and profound idea. Essentially is I don't, if I'm looking backwards, basically I'm thinking, okay, I'm at step 3. How can I reach step 3? I can only reach, then I think about what is my last step? My last step is either take 1 step or 2 steps. If my last step is 1, then it must come in from 2. If my last step is 2, it must come in from 1, right? So you will find out that this is true in general. You find out this is true in general. Essentially, what we talk about here is in here, what we found out is A3 is equal to A1 plus A2 plus A1. So this is the last step is, so this is, oh yeah, okay, I'm just gonna, what? Right? And I will actually find out this is true in general. So if you think about the previous one, so you could have, this guy jump 1 step. Oh my God, this is terrible. Or this one is jumping 2 steps, right? So this is only 2 ways you can reach AK. You're either coming from like, this is 1 steps, this is 2 steps. That's actually reason in general, I will have this. And this is what we call the recurrence relation. Okay, so yeah. Okay, so once we have the recurrence relation, then it's very easy to write the code, right? Because and also we have the initial condition. In this case, we need 2 initial conditions because it depends on the previous 2 states, right? So that's really, but we already know like A1 equal to 1, A2 equal to 2. So from this perspective, we can very easy to write our first version of the solution, which is kind of like we can call the recursion, right? So let's show the code. Right. So you can see on your right hand side, that's exactly the code. Essentially say, okay, when n equal to 1, so these are the 2 initial conditions. We know when equal to 1 and return 1, when equal to 2, return 2. Otherwise, I'm just return, that otherwise the current result should be the sum of, n minus 1 and n minus 2, right? So first is this is in terms of the program correctness, this is a correct solution. Let's see. Oh yeah, okay, yeah, it exists. Okay, so yeah, so if when this guy equal to 45, then it's good. Let's think about, okay. Then we have to think about, okay, so program is correct, but it's running too slow. Okay, that's the reason it cannot passing all the tests, right? If it's wrong, then it won't pass the first. Right. So okay, then let's try to looking at a little bit on deeper on what actually happened behind the scene. Okay. Okay. So let me just using a very quick, let's just use a very simple example to illustrate, what could go wrong here. Okay, so let's think about, when we call A5. A5 we'll call A4 and A3, right? Right. Then A4 we'll call A3 and A2. We will return at A2, so that part is fine. The A3 we'll call A2 and A1, right? In which case A1, A2 will return and go back. The A3 will call A2 and A1. Okay, so this is a very simple example, but you already see something which is not looks very good. Why? Because if you look at this piece, right? This piece is exactly the same as this piece, right? What does that mean? That basically means, okay, I kind of like repeat this piece. I kind of like repeat this part of the computation twice, right? I kind of like repeated the computation twice, right? So so this is the number one thing when you do the algorithm optimization you want to find out. Essentially, is if your program running too slow, first try to figure, okay, do I have something which is like repeated to calculate the same thing, right? So if I do, then maybe I should think about how to not do that, right? How to not do that, right? So so this introducing the first idea essentially is what we call the technical name is called recursion with the memorization. Essentially, the idea is the first time when I call A3, I have no choice. I got to do this one at least once. So I got to do this one at least once. But after I get the result of A3, I probably should save this A3 at some place because this result may be used in the future. Okay, so this is where the memorization part coming from, right? So so then in the second time when I try to calculate A3, I will not do that. I will basically go to my memory to see, hey, do you already have the result for A3? If you do, fine, just give it to me. Then I don't have to do the calculation, right? Everything is sweet, right? So that's like kind of the. So with that to be said, so the one will be look like this. So I still have A5, but now I will put some places here, which is to record my temporary results. Okay, so in here I do A4. Okay, I don't have it. Then I do A3. I don't have it. I have A2. Okay, A2 I already have the result. A1 have the result. So at this point, I will store the result A1. I will store the result A2. Okay. Then when I going back, I will store the result of A3. Okay, then I will store the result of A4. Right. Okay, then when I go to A3, I'm gonna look at here. Do I have it? Yes, you do. Right? You can just directly get your result here, so you will not do any subsequent, calculation. Right? So you can see if this number n is big, then you can save a lot of redundant calculation. Essentially, you make the call. You say, hey, I want the A3. Oh, I already have it. Fine, I'm just get it. So that's pretty relatively straightforward, right? So that's basically is this. So let's see now. Let's see the code. Dun, 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 okay, I think this one is this guy. Yeah. Okay. So yeah. So you see, I'm introducing this actual array. I mean this code is a little bit weird, but anyway. So like, but the idea applies here is the same. So I have this actual array, right? So then because when array is initialized, every element in the array is 0, right? So then looking at this piece, this basically say, okay, I need to calculate I. Then if memory I greater than 0, basically means this value has already been calculated, because if it has been calculated, the result is always positive, right? So but you kind of like the idea. So if this one is already get calculated, I don't calculate. I don't make the recursive call, because this is the recursive call, right? I don't make recursive call. I just directly get the value, then return it. Get the value and return it. If this one is still 0, then I will do my recursive call and save the result to basically memorize the results, then return this one. Then the next time, if I want this one, I don't. So now you see this one will passing all the test, and also the running time seems to be pretty good. Okay, so this is essentially the recursion plus memorization. Okay, so back to the one we talk about here. So this way basically has a kind of like what we call the top-down kind of like a fashion, right? Right, because the recursion is kind of like calling from top-down, right? So DP in some sense is very similar to the recursion plus memorization, but essentially this one basically say, hey, I don't do the top-down decomposition. I do bottom-up build-up. So essentially, you can think about essentially is DP. The idea is bottom-up build-up. So for example, I want to calculate say AN, and I already know AN is equal to AN minus 1 plus AN minus 2. So what I'm gonna do is I'm just gonna say, okay, I start with A1, A2. I can build from A1, A2. I can build A3, right? Then from A2, A3, I can build A4, right? So on and so forth until I build AN, right? So this is what we call the bottom-up build-up. That's the reason, the writing the code-wise, it's also once you have the initial condition plus your recurrence relation, it's very easy to write the code. Okay, so let me just gonna show you what the code gonna look like. Okay, so you'll see here, right? This is my DP array. I have my initial condition dp1 equal to 1, dp2 equal to 2. Then I build up my rest of the value from 3 to n, right? From 3 to n, right? So this is just done by our iteration, then you will get it, right? So then this is your like a recurrence relation. So right, so with the initial condition and the recurrence relation, it's very easy to calculate the rest of them. Then the final one is the one we're looking for, which is, so we just return the value. Okay, so this itself is also pretty easy, right? So that's actually reason. So in here we want to talk about, so both this one and the previous one, the time complexity is kind of like O(n), and the space complexity is also like A(n), because you need the actual array to store. You need the actual array to store, all the states, right? And also that's actually reason DP and the recursion weighted memorization, sometimes we also call you're using space to trade for time, right? So both essentially is space trade for time. Okay. Okay. So so far so good. Then the next thing is, if we're trying to push ourselves a little further, let's so we can probably not improve much on the time complexity. Well, actually, no, that's nothing. So, but in the space complexity wise, we can actually see a little bit, if we analysis a little bit more, then we can actually find out the following. So this is something which is like, what we call the space optimization for DP. Okay, thinking about our recurrence relation, right? Think about our recurrence relation, and also thinking about this DP array, right? So suppose this is the case. So because the way how you fit in the array is from small index to the largest one, right? For example, you fill from the previous one, you fill from 1 to n, right? So then because our recurrence relation say, this one only depends on these two guys, right? When you try to calculate AK, you only need the previous two value. Do you need anything here? You don't really need this. You don't need anything. You don't really need you don't really need anything before AK minus 2, right? You don't need anything before AK minus 2. So basically means this is what we call the DP update, DP update mechanism. Depends on this updating mechanism, it will determine how many actual information you need, right? So if you want to save your space, you only need the two actual variables. You don't need the whole array. Basically, you can further reduce the space from like n to 2. Okay, from n to 2. Yeah. So this is because of the how you're updating the new value, right? Okay, let's see the code. The code is also pretty relatively easy. So essentially, you looking at this guy, okay? Then you realize, oh, I don't really need anything earlier than I minus 2. So I can just do this one. Yeah, I can just do this. I have these two actual variable called one step and two steps. Then this is your recurrence relation. After the recurrence relation, you do update. You properly update. Essentially, you can think about this. You're shifting the one, then that will give you the those value for the next iteration, right? So now this one will only run doesn't really require actual array for the storage, right? So which is pretty good uh, like the improvement. Okay, but okay, let me just recap this one together. So we start with some this particular problem, then we kind of like run through like 4 different versions. Start with the most intuitive, the recursion, the recursion. Then we do, then we plot. Then the second one we add the first optimization by using the memorization. Then we do the standard like a bottom up DP. Then we do the space optimization on the DP. Okay. So recap on the DP. When you think about the DP, really, DP is inside of the divide and conquer, right? So that's actually the reason. A couple of things very important. First one is find the proper way to representing the state. Right? I mean, for this week, the problem we are dealing, the state is very easy to find. Next week, we're going to see some more complicated problem. Basically, the state will be a little bit tricky. If you didn't define state well, then you can't do the problem. But we want to, do this one step at a time. Okay. So the first, I mean, for today's couple of examples we will show later, the state is all very easy to find. And the second one essentially is the state transition, right? Essentially is find the recurrence relation. So these two are probably the key for define a good DP. Okay, so finding the recurrence relation, essentially this is step when you decompose the problem. So just like in the previous case, like my suggestion is when you think about this one, it's always easy to think in a top-down kind of like top-down kind of like fashion, because it's always easy to looking backwards. Essentially, say, okay, I'm at here. How do I get here? Think about the last step. Think about what I can do. What kind of my choice in my last step, right? Then this will break down the current problem, become a smaller problem. Then you're all good, because as long as you break down to a smaller problem at this step, we can establish the recurrence relation. We don't have to worry about how we get to the smaller problem, because we kind of like assuming we already know the result for the smaller problem. We only say, okay, if we know that, how can we use the smaller one to build up the bigger one, right? So, this is these two are the key for all DP. This is the key for all DP. The difficulty is coming in here. Essentially, is sometimes, for example, in some really advanced DP, like the state is very difficult. The state is a very complicated state. Okay, the state is a very complicated state. So, for example, the previous one we see is kind of like what we call the one-dimensional DP, because it only have one variable, right? I mean, today we're going to see another one, which is the two-dimensional one. But you can imagine, it could get very complicated, like 3D, 4D, but whatever. Finding the proper way to represent the state, finding the state transition, these are the two key for DP. Then the third one is, don't forget, the third one is also important, but not as important as the first two. Essentially, is the initial condition. initial condition is important, but most time it could be pretty trivial. So that's reason I'm not. Yeah, the fourth one essentially is the last one we talk about. Essentially is potential potential space like optimization if you find the proper way to update, right? Right. The fourth one is what we call the add-on. It's not the key. Okay, the key is the first one. The key is the first one. The second one. The fourth one is just gonna make the things better, but it's not like So that's reason focus on the first two. Then once you get those one, if you can do further optimization, think about the fourth one. Essentially, say how you can properly reduce the space. Okay, so that's kind of like the web up on the TP. Okay, so let's see our next question, which is kind of like directly related to this climbing chair thing. Okay, so this is a question 7. Okay, so this is okay, so this is a kind of like a directly like the extension about the previously climbing chair. So, but we are looking something slightly different. In the previous one, we're looking at the number of the different way you can reach to a certain stair. In here, we don't actually care about the number of way to reach the stair. We are looking at the minimum cost to climbing the stairs. So now you have to figure out how to calculate the cost, right? The cost basically say, okay, so there's two things here. First one is basically is this. Suppose you are at a stair I, okay? Suppose you currently at a particular stair, then you have choice to either moving one step or two steps, and the cost you will pay essentially is the cost associated with the current stair, okay? Current stair, okay? This is number one. Second one is starting position. You can start either from the index 0 or index 1, okay? So let's look at this one. So first example, as a starter, you can either start as 0 or 1. So in here, they say the optimal solution is you start at index 1. Then in here, you can choose to climbing 2 steps. Then because this one total has 3. If you're climbing 2 steps, you will be reach the top, right? Then the cost you pay essentially is the cost associated with this stair. In this case, it is 10 or is 15. Okay. Let's think about what happens if you if you start at index 0. If you start at index 0, you still have 2 choices. You can either do 1 or 2, right? But if you do 2, you will go to stair 2, but you still need 1 more step to reach to the top. In which case, the cost you're gonna pay is 10 plus 20, which is 30. Okay. So if you start at index 0, then you do 1 step, you reach to index 1. That's probably not optimal because since you can start with index 1, right? So that's actually that makes no sense. So then let's look at the second example. Essentially is you start at index 0, then you jump 2 steps, you reach index 2, then you jump another 2 steps, you reach index 4, then jump another 2 steps into to 6. Now you want to do 1 more, not 2, because if you do 2, you're gonna reach to index 8, which you have to pay 100, right? So that's when you do 1, then you jump 1 more, then you done. So total cost is 6. Okay, so I hope everybody understand the problem. So let's thinking about how to do this one. Since this problem is very similar like the previous one, right? So that's reason the recurrence relation is almost identical. It's just like you need to do a little bit of one, only do one minor, twist. Okay, so again, I mean this scenario still exists. Oh, sorry. Suppose I let an to be the minimum cost to reach still n, right? So as I said, always remember define your state, right? So this is our state. I mean, in this case, it's relatively straightforward, right? Because that's what we're interested in. So, right. So that's the state. So basically, it's the minimum cost to reach to state n. Let's think about how the transition goes. Okay. Transition is still kind of like similar. If this is a k, right? No, so if this is a k, you have only two possibilities. Either you're coming from k minus 1, right? Then what's the cost in here? So in here, the cost would be the minimum cost to reach k minus 1 plus the cost on the scale k minus 1. Right? Essentially, you are saying that I'm at the scale k minus 1. I make a choice to move only one step. Okay, so this is the first case, right? Right. So in here, this is basically say, okay, I'm coming from k minus 2, so I'm looking at the minimum cost to reach to k minus 2 plus the cost associated with k minus 2. Then what I do, I will compare both of this one. I will take the minimum. Or maybe I'm using a different color. That would be easier. I take the minimum, right? So this will basically give me like in my my recurrence relation essentially is the like the yeah. Okay, and also now what is the initial condition? Because I can start off from either index 0 or 1, since I can start with index 0 kind of like for free, right? So basically this means A0 is equal to 0 and A1 is equal to 1. Oh no, A1 is equal to 0. Because A0 equal to 0 basically means I start with index 0. A1 equal to 0 basically also means I start with index 1. Right? You can't go anything less than that, assuming all the costs are positive, right? All the costs are positive, right? So that's kind of like, so with this initial condition, so we can get our the one like sorted out. Okay, so let's see how we actually do this. So, okay. Oh, not this one. I think this is one. So the code will be relatively straightforward, right? So, yeah, I initialize my DP. The minimum cost, right? By doing so, every element is 0, right? Then, so these are the two cases I was mentioning, right? If you take one steps, then this is coming from I minus 1. Then you plus the cost on I minus 1, right? If you take 2 steps, you're coming from I minus 2, then this is the cost from I minus 2. Then the current one will comparing these two values and take the minimum, right? So then return, this. So this is very straightforward, right? Then also let's see a different version of this one similarly, basically using the recursion with the memorization. Yeah. So this one, recursion with memorization, they're using the hash map to remember. I mean, I kind of argue you can using array as well. But anyway, so essentially is every time before you make the recursive call, you want to check whether this one is already in the hash table. If it's already in the hash table, you just return it. Otherwise, you basically calculate these two cases, then find your minimum one, and also put this one into the hash table, then return the value. Okay, so that's kind of like that's reason recursion with memorization and the DP is kind of like very, in some sense, is interchangeable. I would say my personal feeling essentially is from the thinking perspective, recursion with the memorization seems to be easier to understand, easy to think about, because this is kind of like along the way how you decompose the problem, right? But with the DP, DP, the advantage is it's building bottom up, so potentially it can apply some actual optimization, in which case memorization cannot apply, because memorization doesn't really know which value has to store. That's the reason it store everything, right? Because you don't know, right? You don't really know, like you cannot throw away some of the results you computed, because you don't control when this value will be used, right? That's the reason this one has to store all the intermediate value. But the DP, because we can control how we updating the value, that's actually the reason we have a much better control, say, which value we want to store and which value we are okay to throw away. So that's actually the reason I would say thinking like recursion with memorization, but do the implementation still do the bottom up build up. That way, like it can do a further optimization. Okay, so this is for this particular problem. Okay, so okay, let's see. Let's continue with another very relatively straightforward and easy problem, but oh, by the way, I should mention a little bit more. So, so for both of this problem, you from the recurrence relation, if you kind of like, so I'm just asking, from the recurrence relation, does anyone recognize what that recurrence relation will representing, especially in math? Does that remind you of something? Anyone? Like AK equal to AK minus 1 plus AK minus 2. Does anyone see this kind of like thing before in other place? You must see this. Anyone? Nobody? Okay, so anyone know about the Fibonacci number? Hello? Okay, yeah, this is exactly the same as the Fibonacci number. Okay, so then so previously I was talking about the time complexity to compute this one, right? So in here we are saying the common complexity is ON. Because this is essentially the Fibonacci, so using some extra math, we can actually show we can compute this one in a much better way. So there is a one technique I will like teach at the the later class for this one, essentially called binary jumping, to actually accelerate the computation for this. Currently, you have to compute kind of like linearly because you do this one at a time, but you can like using a binary jumping to accelerate this one to log n. Okay, so that's something extra with this. Okay, so let's go to see another example. So this is problem. Oh my God, no. Okay, so this is a problem. Let me see. What is this one? Okay, 62. Okay, so this is another very classical problem, and this is the easiest version. There's several different versions. We will talk about it. This is two of the version. So the idea is very simple, right? So you have a robot originally located at the top left. You want to let this robot to reach to the finish line. The finish is at the bottom right. Right. Sometimes it's like the starting is at the bottom left, the finish is at the top right. But either way, it's the same. So in this particular case, every time the robot can either moving one step down or either moving one step to the right. Okay. Now the question is asking how many different ways the robot can reach the finish line, and also in this particular case, assuming there's no, all the cell is kind of like there's no like optical or whatever. Basically, every cell is like kind of like a free. Well, it's kind of like clean. You can reach that. Okay, so I mean, this question has been like. So let's think about this one. Okay. But let's think about this one. Okay, so again, for DP, we need to define the state, right? So in here, I have a grid. So this is the ith row, jth column. So I define Aij is equal to the number of the ways to reach position Ij from the start. Right, so here's the start. Right, this is the end. Right, so okay, this is the state, which is totally fine. Okay, let's think about this. Okay, because we have a restriction, essentially say the cell every time the robot can only moving, essentially is to the right, or to the or going down. That's actually reason. What does that mean is, in order to reach this particular grid point, it can only go either from here or from here, right? But what are these 2 points? So this one is I minus 1. This one is j minus 1. Okay. So this will, because of this, it will give us the following recurrence relation, which is Aij is equal to A. So this one coming from your left, which will be AI j minus 1. This is coming from the left, right? Then plus, or you coming from the top, which is AI minus 1 to J. Right? So this is our like recurrence relation, essentially, essentially because this is only two, essentially, again, we're thinking about the last step. For the robot to reach IJ, the last step, it's either coming from left or it's coming from top, right? So this essentially gives this recurrence relation. Then with this, then it's very easy to write the code, right? It's very easy to write the code. Then let's also talk about the initial condition. We'll talk about initial condition. So this is our recurrence relation. So because array syntax start from 0, right? So in here, the starting one, there's only one way to int the starting one, right? Then look at the first row, because you can only go from left. There's nothing coming from down, right? There's nothing from down. But this first row, there's nothing on top of it. That's actually the reason you will get a bunch of 1. Similarly, for the first column, because there's nothing coming from your left. You are the first column. There's nothing on your left. So you basically you're gonna get a bunch of 1. All right. So this is kind of like your initial condition. Once you have this one, then you can just fill in your filling your this 2D table, right? All right. Let's look at the code. Code is relatively straightforward. Essentially is this, right? So I'm initialize this 2D array. I'm filling everything with 1. Okay. So this way of solving the initial condition problem, then yeah, start from like basically is start from 1, which is the second element in the second row, right? The second element in the second row, right? So then apply this, recurrence relation, then find it. So many DP has this kind of thing. Essentially, say once you figure out the recurrence relation and the initial condition, the code itself is very easy to write. But you do need to define your state properly, in order for you to be able to write that, right? So that's basically is this. Okay. So okay. So regarding to this particular problem, there's also another very beautiful math solution for this one. I'm not sure anyone knows about this one. Essentially, is if you have n by n, suppose this is n, right? Then if you're thinking about, because first one is you got to think about every step. You can either mark as every step. If it's going down, you can put a D in here. If you go right, you put a R here. Then every pass essentially is a sequence of some D and some R. Essentially, is you need to moving down M steps, MD and NR. So basically, what I'm saying here is if something like D, D, R, D, D, R, something like that, right? So basically, is the number of the D is equal to N, the number of the R is equal to N, right? So every one of this sequence will define a unique path. That's actually the number of the ways become a combinatorial problem. Essentially, you have M plus N total this thing, and you choose M of them. So basically, that's basically the combinatorial N plus N choose N, or choose M, which is the same. So that's basically equal to N plus N factorial divided by N factorial N factorial. So this is a very beautiful math way to think about this one, convert to a combinatorial problem. Well, but yeah. Then in terms of the DP, we talk about 1, 2, 3. We haven't talked about the 4, right? We talk about the 4. So in this particular case, we can also think about the 4. The further space optimization. The first is the number one observation is we kind of store this 2-dimensional array. Okay, let me just do this one. In some sense, you can kind of think about, let's assuming, this is n by n. Oh, I mean, m row and n column. Suppose let's fill this one row by row. So you can kind of argue, you can either fill row by row or you can fill column by column, which is the same. So if you fill row by row, you kind of you feel kind of this way. Essentially, you from small to, then this in the one column you feeling this way, right? So you always fill from the smallest index to the largest index. If that's the case, you basically find out when I looking at this value, I only care about this one and this one, right? So I do not care about anything in here, right? So one directly observation is instead of n by n, I can reduce to 2n, which means I don't need m row. I just need 2 row. Oh my God. Right? So if you fill in column by column, you can find out I don't need the whole table. I only need 2 columns. Okay? So this is the first direct optimization you can do. Then if you're looking at it more closely, you can actually find out you can also reduce the 2 row to 1 row. You can also reduce the 2 row to 1 row. Essentially, is the way how you think about this one is this. Oh no. You can kind of put them at in the same row, because this is the case iteration. So for example, this is k, this is k minus 1. And this is the case row value. This is the k minus 1 rows value. Then the way how you updating is you updating this way. Now check the reason. So for example, this is one you try to update. right? You basically is you essentially is oh right. So this cell corresponding to this cell, right? And this one kind of corresponding to this guy. But with the update, you will overwrite it, right? You'll overwrite it. So then you can kind of like, so this way you can merge, you can fill both in the same row, right? You can merge both in the same, you can merge both in the same row. Essentially, is you basically you using new value to keep overwriting the old one. And because the way, because the direction you're updating, so it is okay to overwrite that one because the one has been overwritten is will be no longer be used. Okay, so that's the key for this. So as well, you can eventually you can reduce the 2 row to 1 row. And also in the extreme case, you can also check MN. For example, if M is large, then M is large, the N is small, then you do row by row. If other way, if M is small, N is large, then you can fill this one column by column, but with the similar mechanism. Okay, so this is a little bit more like implementation detail on how you can further operate this. Okay, then let's see the next one, which is the next version about this the same problem, but you will actually see, it doesn't really change that much. Okay, cool. So I think, so what actually changed? So you still got n by n like grid, right? You're still going from top left to bottom right. The only difference is now in some of the cell you could have this obstacle. Okay, could have this obstacle. So for example, in here, the middle cell is optical, so you can't really. This will certainly reduce the number of the way you can reach it because, for example, you can't go through this cell, or you just can't go through this cell. Okay, then they will give you the optical grid, which is if it's 1, that means this is optical, right? So let's think about how to do this. So all right. So we're gonna still kind of like, okay, we're still gonna using, the state wise, we're still gonna using the same thing. Essentially, it's the number of the ways to reach ij. Okay. Then we're still looking at the same, hmm, right? This part is almost the same. Basically, but we with like one actual thing essentially is look at the recursive relation. Basically, if grid ij is not optical, dun, 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 then This is identical as the previous one. This is almost the same as the previous one. Okay. What happens if this one is an obstacle? Well, then by the problem, basically no one can go to the obstacle, which means the number of the way to reach that one is 0, right? Yeah, so this is the only thing we actually need to change in terms of our recurrence relation. Okay, so so number of state does not change. The recurrence relation, we need to make a minor change. How about the initial condition? So just using one example, say, if this one is an obstacle, right? Suppose this is the first obstacle in the first row, then what's going to happening is you're going to see a bunch of 1, 1, 1. Once you reach here, you will become 0, right? Because you cannot reach the obstacle. But because this is 0, then the next one will be 0 as well, because the only one to reach here is from the left, but the left is 0, so you get a bunch of 0. So this is the first obstacle, right? So that's the reason when you initialize, the first column, you have to do something extra, not just assign 0 or 1, or not just assign all the 1. Okay. With this, then then the code will be very easy to write. Okay. Let's looking at the code. So let's look at the code. Okay. So we got in here the obstacles grid is just we are like kind of like performing on top of the obstacle grid. So we got the row and the column. If the starting cell is obstacle, then you have no place to start. Then you have nothing to then just return 0 directly. Otherwise, there's only one way to otherwise there's only one way to reach here. The way how this one can work is essentially because of the way updating. So we're not going to check him back. Okay. Then this is the one like filling the first column. Essentially, say first column say essentially is this one is 1 if and only if 2 conditions. First one is the current cell is not optical, and you can reach the previous one. You can reach the previous one, right? This is the only condition. Similarly, for the first row, it's the same thing. The current cell is not optical, and you can reach the So in the first column, essentially, you can reach the top cell. In here, you can reach the left cell, right? Then inside of this one, you see the only thing changes this recurrence relation. Essentially, is if this is not optical, I apply my the normal recurrence relation. If this is optical, then this one is equal to 0. Okay, so that's essentially is eventually return that. Okay, so this is also pretty. I think it's a pretty like straightforward one. Okay, so I think that's pretty much I want to talk about for today. And next week we're gonna continue talking about the DP. So let me just do. Next week we're gonna see more, more difficult the DP, and we will definitely talk about the knapsack. So yeah, we're definitely gonna talk about knapsack. So today is kind of like a simple 1DP and also the parser on the grid. Okay, so the second problem we're talking about essentially is the parser on the grid. Next time we're gonna talk about the knapsack. I'm not sure whether we're gonna talk about the longest increasing subsequence, but either way, so we're gonna essentially the idea is we're gonna talk about some like introductory level to the intermediate one. So some really difficult DP problem I'm gonna skip. So because you don't need that right now, okay? Okay. So I'm gonna pause here. Do you guys have any question for me? Okay. If no question, I guess I will see you guys next week. Okay. Okay. Bye.